Metadata is, at its core, machine-understandable information designed for the web. It's a highly structured architecture that gives context to digital objects, explaining exactly what they are, where they belong, and how they function. This data architecture operates simultaneously on three distinct levels. First, it describes the content, the intrinsic subject matter of the object itself. Next, it establishes the context, the extrinsic who, what, why, and how of the object's creation. Finally, it defines the structure, the formal associations between this specific object and other information resources. In the theoretical ideal of modern information science, these three layers would establish a perfectly unified web. Every digital repository would speak the exact same metadata language, allowing all types of data to communicate and be retrieved seamlessly across the globe. But the actual digital landscape we operate in is deeply fragmented. Instead of a smooth, unified web, there is massive friction between different data systems, making it incredibly difficult for one repository to automatically read the files of another. To truly understand how modern information architecture works, we have to look past the fantasy of a unified internet and deconstruct the fragmented, chaotic reality of how data is actually stored. The root of this fragmentation is that different academic and scientific domains require radically different frameworks to track their research. This map shows the web of metadata standards across global repositories. Each cluster represents rules for specific fields. If an ecologist uses ecological metadata language, the data is highly specific. A general repository using Dublin Core cannot parse it. This creates what we can call the Babel problem. As different domains invent highly specific acronyms and schemas, their databases become isolated data silos. They speak entirely different languages, rendering them unable to communicate over the network. This raises an obvious systems engineering question. Why do database architects tolerate and even encourage the creation of dozens of competing metadata standards? Because specialized disciplines demand specialized data structures. A curator cataloging Renaissance paintings needs entirely different data fields than a seismologist logging earthquake metrics. This fragmentation is an intentional feature of deep research, not a bug to be fixed. To see exactly why a single universal standard is inadequate, we have to examine the functional typology of metadata. Different administrative tasks require entirely different layers of data. This chart shows metadata properties. The top row, descriptive metadata, tracks title and author for resource discovery. Lower down, technical metadata tracks file size and compression, ensuring a system can open the object. Preservation metadata rely on checksums to guarantee the file hasn't degraded. This second table details how these functional categories translate into daily administration. Tracking the physical condition of a resource, managing intellectual property rights, and documenting legal access requirements all demand their own dedicated, rigid data fields. A traditional broad descriptive schema like MARC is excellent for cataloging a book's author, but it cannot efficiently handle the hyper-granular technical demands of a digital preservation standard like Primus. Therefore, a single digital object only becomes truly functional when these distinct layers, descriptive, technical, and preservation, are simultaneously wrapped around it. Since we must rely on multiple, competing schemas, we have to build bridges between them. This is metadata interoperability, the critical ability to exchange and interpret data across disparate systems. Achieving this requires solving a major friction point. To exchange a file successfully, systems must minimize syntactic, structural, and semantic inconsistencies, so the receiving node can actually ingest and map the data packet. Without automated interoperability, sharing information requires immense manual conversion efforts by programmers. Even then, transferring data between incompatible formats carries a high risk of permanent data loss. Building these interoperability frameworks is the central systems engineering challenge, preventing the internet from dissolving into millions of completely dark, inaccessible archives. Engineers have developed several structural models to handle this translation, starting with localized solutions, uniform standards, derivation, and application profiling. The uniform standard approach forces libraries to adopt the exact same schema. However, global resource heterogeneity makes this impossible. Alternatively, under the derivation method, engineers take a complex base schema, like MARC, and extract a specialized schema, retaining the core structure but modifying depth. Application profiling is similar. It takes elements from an existing schema and adapts them to create a strict set of policies, tailored entirely to the guidelines of a highly specific local user community. Derivation and profiling work flawlessly for isolated networks, but because they prioritize local adaptation over general standardization, they fail to solve the larger problem of cross-disciplinary integration. To connect data on a global scale, we have to look at complex network architectures. Specifically, the contrast between crosswalk mapping and switching schemas. A crosswalk is essentially a massive translation table. It attempts to identify elements in one database schema and map them directly to equivalent elements in a second schema. But as the number of databases increases, this point-to-point mapping becomes a mathematical nightmare. A network of just 5 different schemas requires 20 separate manual mapping processes, creating a tangled, chaotic web of data paths. Mapping thousands of specific MARC fields down to 15 Dublin Core fields causes severe data loss and equivalency failure. The elegant alternative is the switching schema. Instead of wiring nodes directly together, engineers place a broad schema in the center as a universal hub. Every specialized database maps its data only once, directly to the central hub. This drastically reduces the engineering overhead and minimizes mapping errors across the entire network. We started with an ecosystem of deeply fragmented, domain-specific standards, all intentionally separated to protect the depth of their specific research. The lingua franca acts as a superstructure, built from core attributes common to most existing schemas. By applying this superstructure over the network, researchers can execute complex, cross-domain searches globally, while the individual databases perfectly retain their native, highly granular richness. This complex network capability defines metadata as a dynamic architecture of content, context, and structure. The true technological measure of a modern digital repository is its engineered capacity to translate, interoperate, and export data into the wider semantic web.